Good evening. I'm Chris Brown, the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. I want to welcome those of you here at the Stephen F. Udvar-Hazy facility, as well as the thousands more joining us online. Thank you for choosing to spend your time with us. The John H. Glenn Lecture in Space History is our premier annual event for exploring the role of space, science, and technology in modern American life. Since we started this lecture 2 decades ago, we've been privileged to hear and learn from many notable scientists working on an array of exhilarating topics. Tonight's guest speaker certainly fulfills that tradition of excellence and scientific inquiry. Dr. John Mather and his topic, Opening the Infrared Treasure Chest with the James Webb Space Telescope, has to be one of the most captivating inquiries of our time. I know you are equally as excited as I am to learn more about this incredible new space telescope and all that it promises to reveal. Before we get started, I'd like to extend my thanks to the sponsor of tonight's program, the Boeing Company. Boeing and its thousands of employees have provided enduring and generous support to the museum and the educational programs we host. Our success as America's most popular museum very much relies upon your confidence and care. Thank you. This is an exciting time to be at the National Air and Space Museum. We are just over a month away from opening 8 new galleries at our museum on the National Mall, the first phase of our ongoing project to reimagine the entire museum over the next several years. I hope you'll come by and personally witness these transformative and stunning new galleries when we reopen on October 14th. To ensure a high-quality visitor experience, we will be issuing free timed passes on our website starting at noon tomorrow. Now, without further delay, I'd like to turn it over to our curator and chair of the museum's Department of Space History, Dr. Margaret Weidekamp, who has the honor of introducing tonight's speaker. Margaret?
Thank you, Chris. I am honored this evening to introduce NASA astrophysicist, cosmologist, and Nobel laureate, Dr. John Mather. Dr. Mather began his academic career by graduating with highest honors from Swarthmore College, where he received his undergraduate degree in physics. After earning his PhD in physics from the University of California at Berkeley, he became a National Research Council postdoctoral fellow at the Columbia University Goddard Institute for Space Studies in New York City. There he led the proposal efforts for the Cosmic Background Explorer, which became known as COBE. In 1976, he went to work at NASA's Goddard Space Flight Center as a study scientist, later a project scientist. He became a principal investigator for the Far Infrared Absolute Spectrophotometer on the COBE satellite. And in 2006, he shared the Nobel Prize in Physics with Dr. George Smoot of UC Berkeley for their precise measurements of the cosmic microwave background radiation made using that COBE satellite. According to the Nobel Committee, their measurements not only supported the theory of the Big Bang, but also, quote, marked the inception of cosmology as a precise science. A complete list of his many distinctions and awards would take too much of our time this evening. Since 1995, Dr. Mather has been the senior project scientist for the James Webb Space Telescope, his subject for this distinguished lecture. Dr. Mather also has a special connection with us here at the museum, if I may tell a short story. Dr. Mather generously donated 3 gold-plated bronze copies of the original gold Nobel Prize medal, 2 to NASA and 1 to the museum. NASA encased their copies in beautiful displays, as befits the agency's pride in his accomplishments. However, that meant that the museums was the best candidate when some of Dr. Mather's friends and colleagues at NASA got the idea to send a copy of his Nobel Prize into space. The late NASA astronaut and former Goddard Space Flight Center scientist, Dr. Piers Sellers, arranged to fly it aboard STS-132, one of the final 4 space shuttle missions. Dr. Sellers also personally hand-carried the artifact back to the museum in 2010. Now, as a curator, I will tell you that any object that's flown in space that counts that rare distinction as a part of its provenance, as a part of its history of ownership and use. That has an extra special richness as a museum artifact because it adds to the stories that it tells. In this case, Dr. Mather's Nobel replica already told an important story about his and Smoot's path-breaking work on detecting the background radiation that testified to the origins of the universe in the Big Bang. But I think that as a space-flown artifact, one that was arranged, frankly, on relatively short notice and with considerable effort by his colleagues as a tribute to him, Mather's space-flown Nobel Prize replica now also reminds us of his role as an esteemed mentor and highly respected colleague. As I was writing my remarks for tonight, this quote from Dr. Mather himself seemed like a wonderful transition to the talk. Dr. Mather has said, "Talk to people. Everything good I've done has come from conversations with people. Science is a very social phenomenon." Dr. Mather, we're delighted that you are including us, both our audience here at the Stephen F. Udvar-Hazy Center and those who are joining us online, in that ongoing conversation. Please help me to welcome Dr. John C. Mather as the museum's 2022 Glenn Lecturer. Thank you. The stage is yours.
Thank you, thank you. What an astonishing introduction. And I can't really see you with the lights on, but I am thrilled to be here because this is the museum has been almost my home in a second way. When I first got my job at Goddard in 1976, I came down to the museum in downtown every time anybody came to town, and I made them see the movie. And it was my home. It just is a special spot for us, and I'm a little teary thinking about that connection. So we scientists are emotional too. Anyway, I want to tell you the story of the James Webb Space Telescope, and it's here on the screen. It is a gigantic piece of equipment in space. That golden hexagon you see in the middle is a mirror. It's actually plated with gold. It's made of beryllium, and it is 21 feet across, 6.5 meters. And it is bigger than the rocket, so it was unfolded in space after we got it up there. It is an international project. It required NASA and the European and Canadian space agencies to put it up there with many, many contractors. It took altogether at least 20,000 people to put it together. So when we think about how does something like that happen, well, think back to when did the first humans first pick up rocks and make weapons? When did they first melt a rock and get metal? Think, when did they first melt some rocks and get glass? And how did they remember all that? We are following their example and their tradition and remembering and learning as we go. So anyway, I want to show you what we got. The telescope is up in space. It is working beautifully. It is available for all scientists in the world to propose to use, and the data are coming out. So we'll show you a bit more about it as we go along, but that gray area you see under the golden hexagon, that's a big umbrella. We call it a sunshade. It keeps the telescope cold. Keeps it cold so it can pick up infrared light, and we'll show you later why we want to pick up infrared light. But let me take the next step though and say, well, why did we want to do this? What's cosmology about? So everybody's heard about the Big Bang Theory, which is actually a very confusing name for the expanding story of the universe. So back in 1929, Edwin Hubble drew us a graph. It was the first one that told us about the expanding universe. What's on the graph are little dots. and each dot represents a galaxy. On the horizontal axis, that way, is the measured distance or estimated distance that he had, and the vertical direction is how fast is it going away from us. Well, there's a trend here. Everything is going away from us except for 4 little ones that are coming toward us, and that's interesting. But the trend says the farther away, the faster. Divide the distance by the speed, and you can get the age of the universe. So that's the first time we knew the universe had an age. Now, Hubble got it wrong, of course. His number was too small, and it was a long time before we figured that out. We actually needed the telescope that we named after him to get the right answer. Now we call it the Hubble-Lemaitre expansion law because Georges Lemaitre figured out that this should be true based on Einstein's equations. Einstein said, "Now that couldn't possibly be right." Made a lot of fun of Monsieur Georges Lemaitre, who was actually a parish priest as well as a PhD physicist. And so, anyway, Lemaitre was right. The universe is expanding, and this is the first bit of evidence that we have. So later on, it was labeled by Sir Fred Hoyle as the Big Bang, because he didn't like this idea. But actually, it's true. The universe is still as it is. Things are rushing apart. And we call it a Big Bang because we can't imagine anything else to call it. But it's a bad metaphor because it makes you think of an explosion, like a firecracker, but we actually have in mind an infinite universe expanding, and everything in the universe rushing away from everything else, at least at the scale of galaxies. So there's the story we had almost a century ago. The universe is expanding. So then, following along, 1948, it was predicted that the universe should be filled with heat radiation left over from the Big Bang. And it was predicted that temperature should be about 5 degrees Kelvin, 5 degrees above absolute zero. So it was not measured until 1965 when I was a college student. By the time I was a graduate student at Berkeley, I was mentioned, I'm looking for a thesis project. Well, how about we measure that? Okay, so I worked on a project. My thesis project failed. Did not work properly. But my fellow graduate students made it work again. It worked the second time, and it's actually hanging, or will be hanging again, in the museum downtown. Anyway, this is the map that was made by the successor project, the Cosmic Background Explorer, and it took 1,500 people to build this mission. So again, this is not a small thing. When John Mather is recognized, we, the team, are really recognized. Nobody does this thing alone. And what you see here in the map are pink and blue blobs. It's the map of the entire sky, as you would see it if you had millimeter wave eyeballs and could pick up waves that are about that long. So what we're seeing here is the universe was not exactly the same temperature everywhere, which is to say it's not the same density everywhere, even when it was very young. This is a picture of the universe as it was about 400,000 years old. So, okay, so now we've got the story. The universe is expanding. These were the kind of initial conditions. Well, what happened then? Well, got to go look. So, of course, we built the Hubble Space Telescope. It is still working, thanks to 5 astronaut trips up there, and it's been upgraded numerous times. It is far more powerful than we ever imagined when we were thinking about building it in the 1970s. So now we have its successor. It's not a replacement, it's a successor. It does something different. So here is the new one, the James Webb Space Telescope, going up into space on Christmas morning. And it was a beautiful, beautiful launch. Now, it looks like it's actually dark that day, but it's only because the photograph is set so you can see the rocket. It was morning. It was bright morning. My wife and I sat in our sofa at home watching it go because that was a day of very high COVID contagion. So all of our launch parties were canceled. Go home. Only the people that need to be here, need to be in the launch facility, need to be at the control systems in Baltimore were allowed to be there. So, okay, so it worked. It actually worked beautifully. Telescope was launched exactly where it should go, and we'll show you where we put it. We put it around a place called the Sun-Earth Lagrange point. This was discovered by a guy with a pencil, Leonhard Euler, in 1750. It's a place, along with all those other points in the chart, where the combined gravity of the sun and the earth will pull the object around the sun with us once a year. So it means our telescope can stay 1 million miles away from Earth all the time, and it's overhead at midnight. So that's where we put it, and when the rocket put it there so perfectly, we know that we didn't have to spend any extra fuel to get it to the right spot. So that's why we have a 20-year predicted lifetime. So here is our vision of the 7 minutes of terror that the Mars landers used to have, or do have. This actually took us 2 weeks. We are unfolding the telescope by remote control commands after it was let loose from the rocket. 2 weeks. First thing we do is unfold the solar panels, because we need electricity, about 2 kilowatts. Then we unfolded the transmitter and receiver antenna, so we can talk back and forth at a high data rate. Then we start to unfold the sunshade and separate the telescope from the warm part of the spacecraft. Now we're unrolling, in the video here, we're unrolling the covers that protected the sunshade from dirt and damage. You look at this and just say, this is an incredibly complicated thing. Why did you do it that way? Well, we couldn't think of a simpler way. So it's incredibly complicated. We had to work really, really hard to make sure it would work. So how are you going to make something like that work? Well, you build a little, you test a little. You say, I think I can't really understand this unless I can build it and see it and test it. So that's what we did. Especially the unfolding sunshade there was the hardest part to understand properly, because it's not just a hinge, it's complicated. Cables and pulleys and structures and rods that push out, and anyway, really complicated. But we did it. So there it is in outer space, rotating before our eyes in the video. This is, of course, a view that no human would ever see, because the telescope's in the dark. So anyway, there it is, and it took 2 weeks to do that. Then it was not in focus, of course, right away, because the telescope is still warm. The mirrors have not been adjusted. That big golden hexagon is actually made of 18 pieces. So here's the schematic diagram of this observatory. We see the telescope in the top, the sunshade in the middle, and the sun, not nearly as bright as it really is, below it. And so there it is. Let me see if I push the button here. You should see the light coming in from the sky, being focused down by the mirror onto the smaller mirror, then going into the instrument package, which is on the left-hand side and contains altogether 4 different instruments. And we'll show you what they do more than telling you about how they really work. But they're cameras and spectrometers. A camera just takes a picture. A spectrometer spreads out the light of a subject into a rainbow of different colors, so you can say exactly what wavelength is that light. And it tells you many things. We'll show you. So why would we want to use infrared? Why would we want to see infrared? Well, it tells you something different. So there's a place where stars are being born right now, and there's one in the middle that's sending out a jet of material. So this is the typical picture that the Hubble could take with visible wavelengths. It's got a little bit of infrared capability, and this is how different it looks when you tune up the infrared. The dust clouds are much more transparent. So it's like when you go to the scanner over at the airport and you want to go through, and they say, well, make sure you don't have anything you shouldn't have. Well, long wavelengths, millimeter waves in their case, will go around the fibers of your clothes, so you can see if your person is carrying the wrong thing. We do the same thing with infrared in space. The longer wavelengths will go around dust grains in space. So let us see inside. That's number one reason. Then we also want to see things that are not warm enough to light up when you just because they're not hot enough. I don't emit visible light, I reflect light, but I emit a lot of infrared. I'm emitting about 500 watts of infrared power right now, and you can't see it. But anyway, we need the same sensitivity in space to see astronomical objects that are cool. So these, what we see here is called the Southern Ring Planetary Nebula, and we've just shown you the magnified inner zone of it. This is a debris cloud that's coming out from a star that's old, and it's letting its material fly off into space. So, third reason, why do you want to study infrared? Because space expands. The universe is expanding, the distant objects are running away from us. It means that the wavelengths that we get are longer than they were when they were sent out. They get stretched along the way. So we actually use that to tell us not only one, is the space is expanding and distant objects are going away, but we can use this as a calculator to say, well, if we know how fast they're going, then how far away are they really? So we do that on purpose. So we start off, we take a picture of something, and we try to imagine what it would be like if it were actually at greater distance. Now, we had a movie. Now, okay, it's working. You see, they've animated the idea that the galaxy will look redder if it's farther away. So just let me now begin to show you some of the pictures we actually took. This is the one that President Biden released on July 11th. It is a very long exposure of a single spot in the sky. And so it was observed with our near-infrared camera. Near-infrared camera covering from 0.6 microns wavelength, which is red, and you could see it, out to about 5 microns, which you can't see. And what we see in here are a lot of beautiful things. The thing that might look beautiful to you is that star right in the middle with the 6 spikes sticking out. The 6 spikes are just the result of diffraction of light. Light is a wave, it bends around corners, and that's the pattern that we get from the hexagons that the Webb telescope has. What else have we got in the picture? We have a really big, bright, glowing region in the center, which is a gigantic, very massive galaxy, and it's got several other massive galaxy friends with it. They're pretty far away, but not really, really far away, and they are so massive that they can bend the light of more distant objects. So we're using this as another lens for the telescope. Einstein told us this could happen. He thought we would never find it, but we did. Actually, it was one of the first tests of relativity that the gravity of the sun was able to bend the light of a distant star just a tiny, tiny bit. But this other effect, where you could use it to actually magnify something far away, people guessed, but no, it was obviously impossible to ever happen. But nature does it for us. We have hundreds of these things in the catalog, places where we can look. So in the middle, we see the big bright galaxies. We see some very strange arc-like shapes, which are the magnified images of much more distant objects. So let's go find out what they are. So now we are going to take a spectrum. So what is a spectrum? Well, as you said, we stretch out the light and measure the wavelengths that it has to see its colors. So we're going to do that for those galaxies that are in there using our telescope. So, okay, so here's one. We looked at that image, and there are a couple of little strange-looking arcs. We say, what are those? We think maybe they're the magnified images of a distant galaxy. Well, we got their spectrum, and they said, oh, it's the same galaxy. 2 different images of one galaxy way out there. And what is in it? We've got hydrogen and oxygen in that most distant galaxy. Well, okay, well, that's great. But, you know, we were hunting for and hoping for finding a galaxy that had no other elements in it besides hydrogen and helium. So this is not it. One of the great hopes of astronomers is to understand how did the galaxies grow from the primordial material, which was only hydrogen and helium, no oxygen. So, okay, it's very, very distant, but it's not primordial, not yet. We can't see that far just yet. We're hunting. That's one of our jobs, to hunt for the most distant galaxies we could possibly hope to find and see what's in them. So another way we do this, we have another instrument called the near-infrared spectrograph, which has a complicated way to use it. It's got 250,000 tiny little shutters in it. And you can say, I'm going to open the shutter in front of the galaxy I care about and let the light into the spectrometer. And so that's what we've done here. We have 4 different galaxies that are candidates for being very far away. So each one has about the same kind of materials in it, hydrogen and oxygen. And we see, however, that the wavelengths at which those emissions come in are different for the 4 different galaxies. So we can say how far away are they and how fast are they moving. So pretty fast, but not nearly as fast as we are hoping to find with the even more distant galaxies. So we're hunting for those most distant, earliest ones. So what else is in them? We spread out the light some more. We can find out other elements that are in there, not only the oxygen, but also neon is in here. So where does the neon come from? Neon, oxygen, basically all the chemical elements besides hydrogen and helium come from stars that had burned they've blown their stuff back out into space and enriched the interstellar or even intergalactic medium with those chemical elements. So, well, when we're looking around the room here and we see each other, we say, oh, you're not made of hydrogen and helium. Those elements came from stars too. We are actually made of exploded stars ourselves. Everything in the building made of exploded stars. So you don't think about it every day, but think about it. If you want to put yourself in a cosmic perspective, think like an astronomer. Oh, that's pretty amazing. Okay, so now we can do chemical analysis of those distant galaxies. Then what do they look like when they're bumping into each other? This is an image of something called Stephan's quintet. There are 5 galaxies in the picture, 2 of them quite close together in the middle, and you can see they're in the process of merging together. The one at the top is close to them, and it is going to merge with them, and you can see the red blobs in the middle are the result of stars being born right now. The capability that we have lets us say this is the color to show when we think something like a formation of new stars is happening. So that's a process to reveal how galaxies merge and how galaxies make stars. The one on the left there in the middle is actually not part of the same group. It's a much closer one, but it's so close that we can actually see individual stars in that galaxy. So I just love looking at it because it's beautiful, but it's also beginning to tell us a story. So what's in the black hole? Well, the top galaxy, I forgot to tell you, the top galaxy has a black hole in it. So every big black galaxy has a black hole in it. Our Milky Way has a big black hole in it. When I say big, I mean millions to billions of times the mass of the sun. And what's a black hole? Well, it's a place where there's so much gravity that nothing can get out. Okay, well, how can you see one? Well, you see things that are falling in as things are being pulled in towards the black hole. They are compressed and heated to immense temperatures, and they glow very brightly. So that's what we're looking at here. And quite often there's even a jet of material that comes flying out from the north and south pole of such an object, and we're even seeing that in this picture. So, okay, tell me more about the black hole. What's around it? So again, we do our spectroscopy trick. We spread out the light, we get the chemical constituents, and this time we're seeing iron ions orbiting around that black hole. And we not only can see them where they are, we can see how fast they're moving. And the shapes that are shown for all the different atoms and molecules are different. So astronomers begin to build up a story of how does this thing really work. Of course, when I tell you there's a black hole, it's not like I saw a black hole. I saw a picture and I made a long story and I checked it with my buddies to see if it makes sense. So what else is going around? Well, we want to know what's happening in the neighborhood. So we have signs of dust here. In the lower spectrum there, it says there are silicates. What's silicates? It's sand. So there's sand in space, and that's the part of the dust cloud that makes it possible to have new stars being born. So new stars are being born right nearby to the black hole. That's something that we needed to know. And we're still very curious, because does the black hole make the new stars, or do the stars make the black hole? This is like one of the biggest questions we're hoping to answer. Where do the black holes come from? We know big stars can make black holes, but they're not very big. They're not supermassive. So where did the big ones come from? We do not know. Here's a beautiful picture, and it tells an interesting story too. It's called the Cartwheel Galaxy for a pretty obvious reason. Now we have a story to tell you what made this galaxy. The little reddish one in the upper left went flying right through the middle of the big one. So you're seeing a splash. And what's happened from the splash, the gaseous material has been flung out from the center of that galaxy, and it has caused new stars to be born all at once. So that glowing ring around the outside is brand new stars, all of about the same age. So eventually we'll understand how this works. Right now, I can just tell you it's an amazing picture. Here's a beautiful picture that was processed by a citizen astronomer. I'll show you her picture later. This is a galaxy called M74. Messier saw it from his balcony in Paris in 17-something. This is a galaxy which has star formation happening in it, and you say, why does it look like a sponge with holes in it? And the reason is that new stars have been born, and when the new stars are born, they are so bright that they can burn holes in the neighborhood. We'll show you more in a local version of that in some of our other pictures. So anyway, I just love looking at the picture because it's so, well, if you know what you're looking at, it's very informative. Right now, I can't really tell you all the things that are in there, but we pretty much need a tour guide. And Judy has done an amazing job in making it not only beautiful, but informative. So, I told you stars are being born today. This is a place called the Carina Nebula, and many people have already adopted this picture to be the thing they put on their telephone when they open it up. Carina Nebula. Carina constellation is in the southern sky. You can't see it from here, but this is a place where new stars are being born right now. The new ones in the picture are at the top, and they're very bright and very blue. What we're seeing here is the cloud is evaporating. There's a kind of mist being driven off from the surface of the cloud by the heat of those new stars. And then there are many, many new stars being born, but not quite that bright yet, that are hidden inside the cloud. So I have a little more detail to show you, but maybe I should say, why do we find stars being born in dust clouds? The reason is gravity is pulling gaseous material together, but pressure of the warm gas pushes it away. So a star can only be born when the gas is cold and compressed, and the dust clouds protect the gas and let it get cold. So that's why stars are being born in dusty clouds like this. That means, however, that it's really hard to see them. So infrared, as I say, lets us see inside the cloud, and there are hundreds of new stars, some of them with planets, or probably all of them with planets, being born in that cloud. We have a little more detail. You can see the clouds being eroded by the ultraviolet, burning the mists away. In the right-hand side, you can see something I don't understand. It sort of looks like there's an object there which is sending out jets of material, but the wind is blowing past and bending one of the jets around. Somebody will actually figure out what this is in a while. But for the moment, it's just beautiful and amazing to think about. I mentioned that stars forming in the dense regions. Well, here's a picture of one of the dense regions, and anyway, we'll gradually understand it. It's one of the great mysteries of astronomy. In fact, when I was a young college student, it was not even known yet for sure that stars are still being born. I thought, well, anyway, it took us a little while to figure this out. So the jets come out from the stars. How does that work? Well, when a nebula of gaseous material is trying to pull itself together by gravity, it spins. And jets of material sort of, again, squirting out the north and south poles. And then we're seeing that. In the left-hand side, you see this thing that looks like it has two little ears sticking out. That's because there are two jets coming out, but the wind is blowing past them, and the jets are getting bent around. So that's just one of the more amazing things. In the right-hand picture, you see a similar thing. Jets are coming out, and they're being bent around by the wind in the neighborhood. So we will figure this out. Here's a place called the Tarantula Nebula. Well, of course, it was called the Tarantula because it looked like that in a picture a long time ago. But this is with over 10,000 new stars being born inside there. We will be able to look inside and see the details. In fact, we already have some of them. This, by the way, illustrates the color scales. We have to make up colors. You know, you can't see infrared light. So when I say, is this a true color? Of course not. However, we usually do what's shown in here, that the shortest wavelength that we've observed is shown in blue. The medium wavelength is blue or yellow, green or yellow, and the longest wavelength is red. So that's how they've color-coded this one, so you can make sense of it and remember. So a little bit more detail. The longer wavelength infrared makes a completely different picture. You can see the dust clouds glowing. By the way, what's in the dust out there? Well, it's not only sand grains, but also carbon, various kinds of carbon molecules, organic molecules, even buckyballs. Carbon molecules, a ball of 60 carbon atoms that look like a soccer ball. We find them in space. Amazing chemistry out there. And this is a picture we just got this morning. This is Orion Nebula. Orion is a very nearby place where stars are being born today. That bright star in the middle, in this picture, you could see almost with your own eye. It's in the middle star of the Sword of Orion. And so we know that's a good place to look when you want to do astronomy because it's nearby and bright. And every time we build a new telescope, we always point it there just to see what we can see. So it's a very different picture from what we had with the Hubble telescope. It's still something to be figured out. So there it is, with some more details being pointed out here. You can see, anyway, man, it's just beautiful. And here's the difference between Hubble and Webb. Same things, but different appearance, eh? By the way, you can get all these pictures yourselves. Just download them, go to the webbtelescope.org, I think is the name of the website, and you can find them there. Or just Google JWST images, you'll find them. Well, of course, we don't only look out there, we look closer to home. Here is Jupiter in a completely new picture. So what we're seeing here is especially different from what we can see before. There are auroras on Jupiter. Those glowing rings, the orange and yellow at the north and south pole, are auroras. So we can see them differently in the infrared and try to understand them. The great red spot doesn't look red when you use infrared light. Infrared light penetrates to different depths in the atmosphere of Jupiter. We have other pictures of Jupiter that even show there's a ring. We already knew there was a ring around Jupiter, but it's very thin and very faint. We can see it pretty well with the Webb. We can see all of the satellites of Jupiter. And in fact, we're very interested in one of them. I forgot to tell you, this is the lady who does the image processing. She lives in Modesto, California, and she does it at home. She makes beautiful, beautiful results, and we thank you. Thank you. That's great. Okay, so I mentioned we were going to look at satellites of Jupiter. Here is one that we are very interested in. Galileo himself discovered it with his little telescope in 1610. And we sent a probe out there called Galileo when he took this picture. And this picture shows that this little satellite of Jupiter is covered with ice, and that under the ice we know there's an ocean. Ocean is probably salty, but we're very interested to know, is that ocean possibly alive? So how would you know? Well, when we first found out, we said, we better land a nuclear reactor and melt our way in. Then we found out there are actually water jets that come out from the cracks. If you happen to be watching with a Hubble telescope at the right time, you can see them. So we decided we're going to send a mission out there and fly that right through those jets of water and see if they have organic molecules in them. Well, what do you think? Is it alive? I don't know. I think wouldn't be surprised if it is, but it also could be a hostile place to be alive. That's a pretty unusual living place. But we got to go look. Nobody can answer by thought alone. And we will be going out to Titan. Also, we're sending a little probe, and there's this picture of the helicopter in the lower right corner, which is it's a quadcopter. It is propelled by electric motors. How do you get electricity on Titan? It's really, really far from the sun. It's really, really cold. So we have a little thing called a radioisotope thermal generator, and we get a small amount of electricity from it. We save it up in a battery, and every now and then we have enough battery charge that we can fly. So this little helicopter will be hopping around the surface of Titan. Titan is the only satellite of any planet in the solar system that has enough atmosphere to do this. But it's got about about as much density of atmosphere as we have here, and the gravity is a lot less. So it's not impossible to fly on Titan. So it's also a fascinating place because it has lakes and rivers and rain and clouds and haze. and they're made out of hydrocarbons, ethane and methane. So people often ask me a question, well, if you're going to go look for a life elsewhere, what should you look for? Well, we always say, well, how about water? Because we like water, and everything here that's alive uses water. Well, maybe that's not the only answer, so nature has done an experiment out there on Titan. If it's possible to have some other form that's based on liquid hydrocarbons, well, we should go look. I don't know. I kind of doubt it, but you never know. So it's also just a fascinating place to go because it's the only place that has lakes, rivers, and rain besides us. We will be looking at planets around other stars. So we got multiple ways to do that. One of them is this one, where you watch a star for a long time, and you wait for the planet to go in front of the star, and the planet will block some of the starlight for a while, and then go away. So you can say, okay, if it does it over and over again, I know how long it takes the planet to go around the star, and I can calculate how far away it is, how warm it must be, how big is the planet. So begin to say, is it like Earth? And some of the starlight will go through the atmosphere of the planet on its way to our telescope. So if you can study that part, you can say, what are the atoms and molecules in the atmosphere of a planet around another star? So that's what we're illustrating here, and we have already started to do it. So here's a prediction of what you would see if there's a small Earth orbiting another star, and it absorbs a very tiny amount of the starlight. The picture doesn't say how hard this is, but it is really hard. So Earth has oxygen, water, ozone, carbon dioxide, methane. We should be able to pick up all of those molecules in another Earth. But it's a very small amount because Earth's atmosphere is just a tiny thin skin over a very small planet, so there's hardly anything to find. So we haven't done this yet, but we will try. We simulated, well, what if there's a planet as big as Neptune, about as warm as Earth? Well, it's got a lot more molecules in it. It's got water and oxygen and carbon dioxide and methane, but very different proportions. And you would say, well, that's not like Earth, is it? But you notice we do still have to think about oxygen, because that's not likely to be alive, that one. Well, maybe. Or what about Jupiter, a Jupiter-sized planet? Well, it's a very, very different object. And this is a prediction for what if Jupiter is a lot warmer than our Jupiter, and what would its spectrum be like. So this is how much light of the star is being blocked by the planet. And you can see a spectrum. So, well, we actually did this. We measured a star. It's a very bright star, and it has a pretty large planet going in front of it every now and then. And sure enough, it has water in it. Okay, well, we knew it would be there because we'd already seen it with the Hubble telescope. So this was just a practice shot, really, to say that, yes, we can do the right thing and get the right answer. But to tell the truth, this is a little bit of a misnomer to call it water. We should call it steam. It's very, very warm out there. We have actually taken a picture of another planet. This is a very hard project also because planets are very, very faint compared with their hosts. This is an example of one that's not. This is a very young, hot planet. It's got its own internal heat source, and it's easy enough for us to find it. So we are already starting to take pictures of planets and to look for their molecules. And here I'm just going to wrap up with a weird picture. The picture on the left is something that we took with a Webb telescope, and Judy processed it. It's got this star with rings around it, and not even round rings, but anyway. And we have now a story about how this happens. It's a star that emits a great amount of wind coming out, and when it meets its companion, and they're going very close to each other, they both put stuff out, and we get these pulses that form these astonishing rings. So if you want to know more, there are plenty of ways to find out. We have, of course, websites, social media, and everything else that modern people use to keep track of things. But for now, I think that's my short version of the story, and I'll be very happy to have questions and see if we can answer them. Thank you. Okay. So we're going to do questions over here.
So as we're finding our spot, please find the microphone up in the center of the auditorium if you would like to ask a question in the theater. And we'll be getting questions also from our online audience. But I have to start with, when you were thinking initially about the James Webb Space Telescope, which was initially called the Next Generation Space Telescope, the form of it is so striking. Is your idea of what the form could be? Is your idea of what the function could be? Where does the idea start?
Well, of course, the first question is, what do you want to accomplish? What do you want to see? So astronomers wrote us a little book, a committee report. It was most poetic. It was called HST and Beyond. HST is Hubble Space Telescope. And they said, please build us this telescope because this wonderful science we could do. And by the way, please also figure out how to see Earth-like planets, which is much harder, and we haven't done it yet. But they said, please work on it. So, okay, committee report says do this. Okay, everybody reads it. Well, can NASA do this? Well, of course we want to try. That's our job, to try. Okay, so I got the phone call from NASA headquarters. You want to work on this project? Call up John Campbell. We'll get together, we'll start. Okay, well, how are you going to do it? I have no idea. So, well, we'll just start. So we get people together and talk. It's a social thing, like we said earlier. So I've got an idea. Okay, we'll draw the idea. Oh, that won't work. Well, draw another idea. Oh, that won't work. Eventually, we presented our ideas to industrial contractors, and they said, well, don't just tell us what to build. Let us think. So send us some money, we'll get a study going, and we'll send you our idea. So then, of course, that's what we usually do at NASA. We have a giant competition. And that ran and ended up many rounds of this. We've started in '95, and we ended up choosing the big contractor in 2002. And by that time, they were able to prove pretty convincingly that they could build a telescope, even though a lot was not yet figured out.
We have a question in the audience, and I'm going to let you ask it, and then I think we should be able to hear it on the broadcast.
Okay, thank you. So pretty early in the talk, you were showing the gravitational lens image, and you discussed that 2 of the objects actually turned out to be the same galaxy, and kind of reflected across that image, there was 2 more very similar objects, and so was it actually 4 copies of that galaxy?
I think in that case there were only 2 copies of that galaxy, but there were other galaxies that also had appeared in multiple places. So if you were going to build a magnifying glass, you would not like that. But it's the ones that nature has given us, and we use them. We've got hundreds of them to use. So we just have to figure out what is the magnification pattern of every one of those lenses that we have.
Young, who inspired you to study space?
So the question that is coming from, can you tell us your name and your age?
My name is Lucy Herwick, and I'm 11 years old.
This is from Lucy, who is 11, and she would like to know who inspired you to like science when you were young.
Who inspired me to like science? I think the museum in New York. I lived in New Jersey, so the one in our area was the New York City.
Yes.
So the Museum of Natural History with the planetarium show and the dinosaur bones. Of course.
Museums are wonderful that way.
Yep.
Very good. That's an excellent question.
I'm not near a microphone, but
I'll repeat it.
try to speak up.
Okay.
So the Hubble had the deep field image, which was pointed, near the Big Dipper, and it was pointed there for I think 30 days and showed us galaxies in the darkest, the darkest field of space. And that image pretty much changed everyone's view of everything. Is there anything planned like that for, the James Webb Space Telescope?
So for our audience at home, the question was about the Hubble Deep Field image, which was so impactful, and what is planned for James Webb Space Telescope that might have that same kind of impact?
Yeah, absolutely. In fact, the Hubble Deep Field image was the first major inspiration for building the Webb telescope. The astronomers looked at that picture and said it's great, but we can't see the first galaxies after all. The telescope wasn't big enough, and it could not see the infrared. So please build us the new telescope. And so they wrote the book, and we did. So On the other hand, we can take the picture that took them weeks in a few hours with this new telescope. So we do overlap the wavelength range, so it's not exactly the same. We're not replacing them, but we can do a most astonishing things. We can see so much better so quickly. So that's one of the reasons we built it, exactly because of that. We have many, many such places in the sky to look at.
Okay.
Good evening.
Good evening.
Thank you for that wonderful lecture. It's been a lot of fun. I had a question about something that I think started with the Chandra telescopes, where we're translating visual data into audio data. And it seems to make sense to me how the frequency and amplitude are being translated, but how are you coming to the conclusion for the timbral aspects of the data?
The question is, if I'm going to get this right, from the Chandra Space Telescope and the relationship between amplitude in terms of sound and in terms of light wavelengths, how are you dealing with that with James Webb Space Telescope?
Well, I think there's actually more to the question than that. Recently, people have tried to make a sonification of the images. And so I haven't read up or listened to them yet, so I can't really answer your question. But if you look up sonification of images from astronomy, you'll find out a lot more online.
Okay.
Thank you.
Thank you. Excellent question. Take the one up at the microphone, and then I see a hand in the front.
How long do you think it'll be until we have the better technology to see the farther galaxies?
How long do you think it will be until we have better technology to be able to see farther galaxies? Can James Webb Space Telescope do that, or is there a next generation?
Well, okay, good question. We've got the best technology we can imagine right now to see the most distant galaxies. So the biggest question that's open right now is how far away are they? How hard do you have to work to find those first ones? And what did nature do to look at? So we built something that's capable of seeing a certain brightness at certain wavelengths. And so we think if the universe made galaxies when it was only 100 million years old, then we should see them. So that's when the wavelengths are about 20 times as long as they are now.
Okay.
So a redshift of 20 or so. So huge expansion since that time.
Mm-hmm.
So, but did nature do anything? Well, we actually are getting a bit of a surprise already, because the picture that I showed you is already telling us that galaxies grew much more quickly than we thought they would. That was also the same surprise we got from the Hubble. Hubble, a picture of the deep field, showed galaxies grew very quickly. So build us another telescope. Well, okay, we'll probably build as much of a telescope as we can manage for now. The next one that astronomers are wishing for is intended more for those little planets. Please build us one that can see little Earth separate from the dot, from the star. So we can see, does it have oxygen, chlorophyll, water, carbon dioxide, methane, all those things that we think represent life here. Is there any out there?
Okay. Very good. I saw a question in the front here.
Very simple question. We often hear that James Webb will help us understand better, dark energy and dark matter. Can you give us a little bit of example of measurement that could, kind of lead us understanding a little better?
Yeah, so.
Will James Webb Space Telescope be able to help us to understand dark energy or dark matter?
Yes. What we can do is measure their effects. As far as we know, there is probably either zero or very small chance of ever seeing them here in a lab. We've been working at measuring dark matter in the lab for decades, and there's not one trace of it yet. So maybe we just don't get to be lucky about that. Or maybe we will. What we can do is measure the effects of their gravity. So dark matter is much more abundant than ordinary matter. So when I showed you the picture of the gravitational lenses in that very first image that President Biden put out for us, most of the matter that's doing that is dark matter. So we can tell you where it is and how much of it there is and what it's doing. how did it get that way? That's the big question. Is it hot? Is it cold? It seems to be cold, but what does that mean? So there's a lot of stories you could tell about what is the dark matter like. Currently we're running on a picture that says there's only one kind, but there's no particular reason that nature should be so simple. Why would it be simple? We didn't ask for this in the first place. Dark energy is similar. There's no particular reason there should only be one kind.
Okay.
So what we get to do is measure, and then we'll argue for a long time.
Yes.
Hi, you mentioned about the NASA folks working on the Hubble telescope. I want to know who's going to go work on this one, and can I go with them?
Who's going to go work on this telescope? And the answer is we're not sending anybody that we know of. It was not designed to be fixed. You can't get it apart easily. No user serviceable parts inside. So we did, however, paint a pattern on the end so a robot could go there and latch on if we could ever figure out what to do. So we are currently not expecting any reason to go there. We are predicting a much longer life than we were hoping for, and we are getting much better performance than we were hoping for. So I think astronomers are going to ask for next is another telescope that does something different, like look for those Earth-like planets.
So
By the way, we are planning another telescope to look specifically at the dark matter and the dark energy coming up in about 2027. It's called the Nancy Grace Roman Telescope. It was named after our first chief astronomer at NASA headquarters. So anyway, in honor of her.
So from our audience online, I've got a couple of questions about these named telescopes. So we have Petra, age 7, is asking how big is the James Webb telescope? And then we also have a question about what does James Webb have implications for Hubble? Is Hubble going to be retired because of James Webb? So how big is James Webb,
Okay.
and how does it affect Hubble?
Right, so James Webb Telescope, the mirror hexagon is about 6.5 meters across. It's 21 feet. So it's about 2.5 times as big as the Hubble telescope, which is 8 feet across. So it's a whole lot bigger. And of course, also the Hubble telescope is contained in a tube. It's protected like a telescope should be. But the Webb telescope is naked out there. It's protected only by an umbrella. So it is a huge umbrella, as big as a tennis court. So anyway, we did it that way because the telescope needs to cool off by sending its heat to outer space.
I was just going to ask, was there a point when James Webb Space Telescope was going to be enclosed, or had always the idea been that you would have it exposed to space?
We always knew it had to be a wide open telescope.
Okay.
Of course, our first decision was, does it orbit near the Earth like the Hubble, or do we have to send it far away? The answer was, it cannot get cold enough near Earth.
Okay.
So it cannot make a giant refrigerator, so better send it far away.
So we've got a question from online about, is there going to be a peak in telescope technology? Is this kind of the best that we can do, or do we think that there could be even more and better?
Hard to answer that. I'm not real good at predicting the future, but there's a huge desire for more. And we have such tantalizing questions that the wheels are turning on astronomers' minds to say, well, if we could build this, could we see that? And the answer is yes. Well, why don't we try? So I've got my own ideas. I've got a weird idea. What about if we could put a star shade in space and cast a shadow on a telescope on the Earth? Why would you do that? So you can see the planets around the star. If you could block the starlight but not block the planet light, you could do that. Well, this is hard. It's crazy, but why not try?
So we have time for another question or so. So we've got a question from in the audience, and then I've got one online.
Thank you. You mentioned that you give off 500 watts of infrared, if I heard you right, and I'm wondering if anything that you've seen in your work has changed the way you look at yourself or us as humans.
Oh, my
So
goodness.
the question is in relation to
Perspective.
how much perspective, and given that you have said that you give off infrared radiation, has it changed how you think about yourself or our place?
Yeah, it is not specifically because of working on this project, but I think about the nature of life and where does it come from. I read about evolution and of course astronomers want to know this. We want to know what to look for if we're going to answer the question, is life rare or common? So I've come to the guess, this is only really a guess, but a guess that life is more like a thermodynamic imperative than a rare event. When I was a kid, astronomers and physicists generally thought, we can't understand this complexity that we see. It must require extremely unlikely initial conditions and special circumstances. And now we've discovered that there's life everywhere, that there's water. So how special is that? Well, is water special? Yeah. There's not everywhere, but so now I have a different guess, that life will be everywhere that it's water, liquid water. And so now the biologists are beginning to think this also. So that's a big change.
So I want to ask then the last question for the evening. About a decade ago, you were asked what we might expect to see from the Webb telescope, and you replied, things we can't even imagine yet. So what have you seen that has surprised you the most so far?
Well, I guess what I hadn't imagined at all was how beautiful the pictures would be. Oh, we knew the numbers. We can calculate some numbers. We can't calculate that picture. So that's the first surprise, is how beautiful things are. And then, technically the big surprise is the galaxies grew so quickly. We thought we knew, but we didn't. So that's a great surprise, a pleasant surprise, because that's what we thought. We had to guess what to look for, and we found something already in the first weeks.
That's wonderful. Thank you so much for sharing that with us. Let me turn it back over to Chris.
You know, I'm struck that there are times in our lives when we have these moments of where you've been somewhere special, and I think tonight qualifies. To be with you, Dr. John Mather, to hear from you, and see the evidence coming from this remarkable technology is just a privilege. And again, please join me in thanking Dr. John Mather and the entire team that came together to allow us to enjoy this evening's talk. And to our online audience, I hope this is motivation to come visit us. As mentioned, we will be opening 8 new galleries downtown on the 14th of October. I hope all of you will come enjoy what we've put together. I think you'll be suitably impressed and surprised. And I will close by saying none of this happens without the support of our community, of the nation, and specifically tonight, the generosity from the Boeing company. If not for their commitment and their generosity, we would not be able to enjoy this evening. So to my partners at Boeing, thank you again. And a word of warning as you depart this evening, don't spend time looking up into the skies, as we might be motivated to do. Drive safely, and stay tuned. More to come, and I hope you'll join us for future programming. And for those of you here in the audience, the surest and safest way out of this auditorium is up the stairs to the rear. Thank you again for joining us. And one more time, thank you, Dr. John Mather.